My name is Shantanu Basu, and I'm the chair of the Department of Physics and Astronomy. I again extend you a very warm welcome. It's our pleasure today to welcome you to the Theoretical Physics Distinguished Lecture, and it's given by Sir Anthony Leggett of the University of Illinois at Urbana-Champaign. The aim of our series is to bring leading ideas from the world of physics to you, the general public, and the university community. I don't need to sell this talk actually, right? I think you're here because of who is speaking. It's obviously a very exciting talk about one of the most successful theories of all time, yet a very widely counterintuitive theory. I'm talking about the theory of quantum mechanics. This event is possible because on campus we have a collaborative program in theoretical physics, which is actually a unique program in Canada. Not many places actually have a degree in theoretical physics. It's a joint venture of the Departments of Applied Mathematics and the Department of Physics and Astronomy. So I'd particularly like to thank two persons for helping to make this event happen. Professor Mahi Singh, Director of the Collaborative Program in Theoretical Physics. Professor David Jeffrey, Chair of the Department of Applied Mathematics. Thank you. This event actually also caps off a two-day conference on the topic of nanostructures and condensed matter theory. And I'd like to again welcome all the delegates here from that conference. I believe it was a very successful conference. Congratulations. I'll mention that the physics community at Western is actually quite broad and spread over several departments and units. And it specializes in many, many subjects, including astrophysics, condensed matter physics, atmospheric, planetary physics, and geophysics, as well as particle physics and medical physics. I hope I don't left anyone out. But it's a very broad field. We also have many philosophers who are interested in the philosophy of physics. So I would say collectively we have one of the largest physics communities in a Canadian university, and we're very proud of that. So on behalf of the entire physics community then, let me welcome you again. And at this point, let me ask our president, Dr. Amit Chakma, to introduce Sir Leggett.
Thank you, Professor Basu, for your introduction. While it is not every day that we get a Nobelist to visit our campus and to speak before us, so it is a great honor to be here to welcome Sir Anthony Leggett to Western. Before I formally introduce Professor Leggett, let me welcome everyone, including our many guests from across Canada and around the world participating in the International Conference on Frontier Topics in Nanostructures and Condensed Matter Theory. Of course, we wish that we could welcome you in a wonderful weather, but nevertheless, we are grateful to you that you have embraced this challenging weather condition to be here to listen to our speaker. I want to thank the Department of Physics and Astronomy, the Collaborative Program in Theoretical Physics, and the Faculty of Science for sponsoring this distinguished lecture series. Events such as this one are just wonderful opportunities for us to bring people together from across disciplines so that we can exchange ideas, learn from each other, and of course at the end of the day, they help us, they help all of us who have the task of educating our future generations to help open their minds. So I'm so pleased that we have so many students who are here, and I hope that you all attend all the lectures with the kind of seriousness that you have taken this one, so that will all serve you well. So congratulations to all the members of the organizing committee for a job well done. With that, let me turn to the main task, that is introducing Sir Tommy Leggett. Of course, he needs no introduction within the physics community, but it is worthwhile to point out number of his many achievements. So I'll be brief. Those of you who don't follow Sir Leggett's career, he currently holds the prestigious MacArthur Chair in the Department of Physics at the University of Illinois Urbana-Champaign, where he has been on faculty since 1983. Born and educated in London, England, Professor Leggett is an Oxford alumnus who is widely recognized as a world leader in the theory of low-temperature physics. And his pioneering work on superfluidity was recognized in 2003 with the awarding of the Nobel Prize in Physics. Knighted by Her Majesty the Queen in 2005 for his service to the field of physics, Sir Leggett is a Fellow of the Royal Society in the United Kingdom, the American Physical Society, and the American Institute of Physics. He is also a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, and a foreign member of the Russian Academy of Sciences. Among his many current interests, Tony is focusing on the design of experiments to test the theory of quantum mechanics at increasingly larger scales. Quantum mechanics has confounded practitioners from its very beginnings, but the most natural interpretation of the theory implying that no definite outcome of an experiment occurs until the act of observation. Tony has been challenging the scientific community to devise tests to determine if these counterintuitive features continue to apply at the macroscopic scales of everyday life. So that's the scientific part of Sir Tony Leggett. I had the great pleasure and privilege of getting to know Tony through a wonderful encounter when I was visiting Tony in his office in Urbana-Champaign, with the lofty goal of trying to get his attention to something that was unfolding at my old institution in Waterloo, something called Quantum Physics Perimeter Institute for Quantum Computing. So we had a pleasant conversation. Sir Leggett is very busy, and Sir Tony, I should say, is very busy. So we couldn't get an appropriate time to meet. So politely suggested, why don't you tell me why you want to see me on the phone? So I said, sir, I can't really explain why I need to see you on the phone, so I'm going to come down to see you. So we sat down. My proposition was for him to give us some time. Sometime, of course, at that point in time at Waterloo. So I suggested that, ideally he would like 100% of his time, but I would settle for anything, as long as it's not zero. So I remember, Tony, you telling me very politely, you're a wonderful human being. So, well, chances of me giving you full time is probably not that great, but chances of me spending some time at Waterloo is something that we can talk about. So that's the wonderful exchange we had. At a personal level, the kind of things that we all admire in human beings, Sir Tony has them all. Apart from his scientific contributions, the other contributions he makes is just through these sort of lectures. He travels around the world, sharing his ideas, inspiring people. So although I'm not a physicist, I can tell you that, in my own world, that I've been inspired just by talking to this man. So those of you, our students who are here in the audience, is a wonderful opportunity to get to know a wonderful human being, a great scientist. So ladies and gentlemen, without further ado, Sir Tony Leggett.
Thank you very much, President Chamberlain, for that kind introduction. It's a great pleasure to be here. If at the beginning of the 21st century, one were to take a survey of my discipline, that is physics, I think you would conclude that for the last probably 80 years or so, it's been in what the late philosopher and historian of science, Thomas Kuhn, would have called normal science. That is, the kind of science in which the kinds of questions you're allowed to ask, the sorts of answers you're allowed to give to them, and the nature of the evidence and arguments that you're allowed to provide in favour of those answers, all of those are pretty much widely agreed in the community. So, at first sight then, you wouldn't expect debates among professional physicists about technical questions in physics to engender the kind of high emotion and personal involvement that we're so used to seeing in debates, say, on politics or the social sciences. And yet there is one such question which generates precisely such extreme passions. And when I was young and mischievous, I used to go to physics conferences, and usually they'd have a little warm-up party the evening before, and so I'd select a group of physicists and throw this question into the conversation with a hand grenade and stand back to watch the results. So what's the question? Well, in the mid-20s of the 20th century, physicists, having totally failed to understand matter at the atomic level in terms of the familiar so-called classical concepts which they were used to, they came up with what's not so much a new theory, but a whole new way of looking at the world, which we call quantum mechanics. Over the last 80 years or so, quantum mechanics has proved successful beyond its founders' wildest dreams. Just about everything we know about matter at the atomic and subatomic level is formulated in the terms of quantum mechanics. It's made numerous predictions, some of them very bizarre and counterintuitive, which nevertheless have been experimentally confirmed. And yet, there is a major problem. After all, most of us believe that everyday things like chairs and cats and even our own bodies and so forth are composed of electrons and atoms. So if quantum mechanics describes accurately the world of electrons and atoms, then presumably it should, at least in principle, describe these everyday objects made of them. We may not have to apply quantum mechanics to the everyday world, but at least it should be possible to do so. And yet, if we do, we appear to get some very bizarre consequences indeed. Is that a problem? This is where the fun starts. To show you how strongly held and how widely divergent views on this question are, let me quote from memory a couple of passages. I won't get it exactly right, but I think we'll get the gist. The first is from the end of a paper written by